Hello.
Hello.
Yeah, so Santosh, we were just shouting at you like a few minutes ago. If you know what to talk about, take it away.
Okay. Okay, I'll just jump right into it. Usually, when we're dealing with quantum mechanics, we take the hermeticity of the Hamiltonian as one of the fundamental postulates. And if we trace back the reason as to why we require hermeticity, there are three main reasons. The first obvious reason is that a Hermitian Hamiltonian guarantees real eigenvalues, energy eigenvalues. Number two, hermeticity of the Hamiltonian guarantees unitarity, and that is the norm is conserved in time. And the third condition is that the eigenvectors of a Hermitian Hamiltonian span the Hilbert space we're talking about.
Right.
Now it turns out that in recent years there have been some studies done in which each of these three conditions can be satisfied in arguably very dubious ways, if you ask me. But each of these three conditions can be satisfied in non-Hermitian Hamiltonians as well, as long as they obey PT symmetry. P is parity, T is time. Now the point is, it's not just PT symmetry. All we need is that the Hamiltonian, there should be one symmetry which is generated by unitary operator and another the symmetry which is generated by anti-unitary operator. The usual candidates such as parity and time reversal. Now, how the mechanism works is something like this. Like
Santosh,
the
just a moment. Why do you need two symmetries? One generated by unitary and one generated by an anti-unitary. I know that both of these are symmetries, like either unitary operator and anti-unitary operator. But why do
hmm,
you need both? I don't understand the statement. Why?
I really do. I've just started reading on this subject. Even I'm not too clear as to how the entire thing works out. You see, the thing is this: with both of these symmetries, there is somehow a way so that you can define a new operator called C. And it turns out that now the Dirac norm, if I redefine it to be bra psi and then this one C operator and then ket psi, this quantity is invariant with respect to time. In other words, I don't define my norm as just bra psi ket psi. I can redefine my norm as bra psi this operator C and ket psi. And this is invariant in time. And it turns out that whenever a Hamiltonian has both these P and T symmetries, then such an operator C can be constructed in some way. And turns out that the C operator, as the notation suggests, is somewhat analogous to charge conjugation. Yeah, that's what I'm doing right now.
Can
Essentially, so if you have a non-Hermitian Hamiltonian, the first problem you would have is the fact that the norm is not conserved in time, which is one of the axioms of quantum field theory, quantum mechanics.
Hmm.
And now you're saying that under some certain conditions, you can have a new definition of a norm, which is still preserved
Hmm.
under time evolution with this non-Hermitian Hamiltonian.
Yes.
yeah, I have two very stupid questions. One, why is hermeticity related to unitarity? I do not see the connection there. Is this like something very trivial that I'm missing?
Yes, sort of.
No, because I can see why unitarity is like useful to like maintain the inner products, but I don't see.
Because if you take if I mean a very simple thing to do would be, for example, write a unitary operator u. It's, let's say, it's part of some D algebra. So now expand this about the identity as some 1 plus I epsilon t or something, and then you'll see that t is guaranteed to be Hermitian if used unitary. So in some sense,
Acha, हाँ,
Hermitian operators
right.
generate unitary transformations. Now, if you want time evolution in quantum mechanics or quantum field theory to be unitary, you require the generator of time translations to be
Hmm.
Hermitian. So this forces the Hamiltonian to be Hermitian.
Hmm. Acha. So the second
So
question.
it's just that
Second question is so we know that CPT is a symmetry of all quantum states. So isn't that like the thing that you were describing, that you change your norm to be something bra times C times a ket? And
Dude, I actually don't know about that. Actually, why is it that CPT is a combined symmetry that is respected by all quantum field theories?
so
Or
it's like
I've
very,
heard something like that.
so it's like you can check it like explicitly, but the easy way to see this is that if you look at the C, P, and T operators, and if you sort of Wick rotate your
Hmm.
like if you work in Euclidean space, then the action of CPT essentially is a
Hmm.
rotation. Yeah, basically
Okay.
that. So it's basically just
So
rotating your states.
basically, every field theory I write down has at least has at least one symmetry, and this symmetry is CPT.
Yes. So it's basically saying that if you
So
have
can I say that?
if you have a ray on a sphere, then that like it's this system is invariant under rotations of the sphere. Basically the same argument in 4D.
Right.
So CPT is essentially
Right.
a
Is
rotation.
this a 4D? Is this
Yes.
specific to 4D, or is it
Yes, yes,
specific,
yes.
or can it be generalized to arbitrary dimensions?
So in arbitrary dimensions, uh, the combination CPT itself, like you can have some combinations. Maybe only CP is um, yeah. I mean, you can form various combinations that will respect the symmetries in various other dimensions. But in 4 dimensions, CPT is like a symmetry of the quantum states. So what I was saying is that since CPT is a symmetry, if you essentially if you define your norm now by taking the C out of the CPT, then you are just left with something that
Hmm.
has a PT, right?
Yeah.
So isn't that essentially what you were describing right now?
Yeah, I think that is exactly what I'm describing.
I see. Okay.
But I do not know the quantum field theory business of this. So
I
I
think
really cannot comment on that.
this is a good opportunity for us to ask Chetan to talk a little about breaking of CP, because he has worked on related areas
I
at some time. I think
It's weird that you
it's
asked me this because I have totally forgotten everything about it. But
yeah. I assume you did it when you were working on the neutrino mass problem. That's
yes,
when I thought.
and that was a bad time in my life, so I tried to forget everything that is associated to that part of my life. But okay, I can describe something. So I can probably describe neutrino and neutrino mass problem, something like that. So essentially, if you want to describe the standard model, the so essentially, if you just start with some local gate symmetries, uh, what you learn in standard treatment of gauge theories and quantum field theories is that if you just start off with a particular symmetry, and if you want that symmetry to be a local symmetry of your Lagrangian, you can end up with a gauge theory that's describing that system. For example, if you have a very simple system, say you have a fermion that's described by some Dirac action, Dirac Lagrangian. Yeah. And suppose if you just say, what if the fermions that I have, they are symmetric under some a global U1 symmetry, say, or some phase change. You can see that this global U1 symmetry is actually a symmetry of your system, and you don't learn much new information from this except the fact that you can associate some quantity known as a charge that you can define by Noether's theorem, and that would be globally conserved in your system. But the interesting thing happens when you uh, impose this symmetry locally on your system. So what if you say that the system is invariant under uh, a local phase change, or if you parameterize your phase by some angle phi, right? Basically, if I write it as e to the power I phi, what is my phi is a function of the space-time coordinates. So when I impose this symmetry locally on my system, what I end up is that to like maintain this symmetry, I'll have to introduce some new degrees of freedom in the system, and those new degrees of freedom will essentially be uh, the gauge fields or the electromagnetic field. And you can like this can be worked out very easily. And what you realize is that the effect of doing this local symmetry transformation on your matter fields essentially amounts to doing a gauge transformation of your electromagnetic fields. So that's the like cool idea in standard model, that you can just impose some local symmetries and you can end up with some uh, gauge theories that describe your system. Now, what particle physicists realized in 1970s was that if you impose three local symmetries, uh, that can be written as something of the form U1 times SU2 times SU3. uh, like this seems like a very arbitrary combination, but essentially if you impose this local symmetry on your Lagrangian, you end up with a system, like you end up with a set of gauge theories and matter particles that essentially describe everything that we see in the world around us. So the U1 part very roughly describes the electromagnetism. The SU2 part very roughly corresponds to the weak force, and the SU3 part it describes the strong interactions. and like the rest of the stuff is the matter content or the fermions uh, uh, in your nature or whatever you see around you. So essentially, if you write down a Lagrangian that is made up of the fermions and the fermions that you see, the electrons, muons, and stuff like that. And if you impose this local U1 times SU2 times SU3 gauge symmetry on this, you end up with what is called as the standard model. I mean, it's not very straightforward like that because like there is something non-trivial that happens in the U1 times SU2 sector. So what Weinberg and I think Glasgow and someone else, I don't remember the name. So these three people, what they realized was that actually this
I think
U1,
it is Salam.
yeah, exactly, Abdus Salam. So these three people
Hmm.
realized that essentially this U1 and SU2 were not uh, very disjoint sectors. So at some very high energy scale, what happens is that there is a combined symmetry, like there is a unified symmetry in the system, which can be described as by some SU2 times U1, which is different from the SU2 and U1 in the low energy limit that we see, and that is called as an electroweak symmetry. And then what happens is that like essentially as you lower your energy scale, or uh, in a very colloquial way of saying, uh, as the system cools down, what happens is that a symmetry breaking essentially happens, and you can sort of see that there is some mixing that happens here. So the U1 describes uh, some gauge bosons, something that seems like electromagnetic field, while SU2 describes some three set of gauge fields, uh, because essentially SU3 has three generators, SU2 has three generators, and so what happens is that there is a mixing between
These are, by the way, the W and Z bosons. If
no,
somebody wants
actually
to
at this
correct.
point they are not. That's why I said something non-trivial happens. So essentially, at the electroweak level, these are very different. The three generators of the SU2 and the one generator of U1. So they are some. I think they are called electroweak photon and electroweak something bosons, something like that. But while the symmetry breaking happens, a mixing happens between these bosons. So the photon from the U1 combines with a combination in the SU from
Right.
SU2.
Right.
So the
Right.
three generators in SU2, you can sort of write them as some linear combinations of each other. Like that's just a way of doing the calculation in an easier way. So essentially, what happens is the photon from U1 combines with some boson from SU2, and so you essentially are starting with 2 degrees of freedom. So you have to end up with 2 degrees of freedom again. So that linear combination will form something that will look like the actual photon in the low energy limit, and what will look like I think the Z boson in the uh, low energy limit, and the remaining 2 degrees of freedom will also combine with each other to form the W plus minus bosons. So at low energy limit, it's somewhat different from the essentially the field content at the electroweak level. And the reason this
Yeah.
mixing is important is because this is the exact reason why the photon is massless, but the W and Z bosons are not massless. They are massive because essentially
Yes. Exactly.
the linear combination that corresponds to the photon is orthogonal uh, to the essentially the matrix that leads to the Higgs mass. So if you look at the Higgs mechanism, then the Higgs field itself is kind of a, a doublet. It's a doublet field with complex entries. And so if you look at the entire Higgs mechanism, which is very boring to describe here, you will see that this particular combination is orthogonal to the states that you want to look at, and that's why it remains massless even after the uh, Higgs field results in a symmetry breaking. But whatever. Uh, the point is that SU2 times SU3 times U1 is a local symmetry of standard model, and the matter content in the standard model consists of some I think three generations of leptons, uh, each of which contains two sets of particles. So we have the first generation is the electron with the corresponding neutrino, then the second is mu1 with its corresponding neutrino, and third is the tau with its corresponding neutrino. Now the point is that in when you like if you look at the standard model and the fermion content and how the states in the standard model or the various fields interact with the matter, you realize that it makes sense to form like these the doublets that we are talking about the electron and the corresponding neutrino. These doublets are essentially what act as the fermion fields in the standard model Lagrangian. And the point is that this standard model itself is a like it's a chiral theory. So the W plus minus bosons, essentially the weak part of the standard model, it acts on chiral states. So the point is that for massless particles, chirality, this helicity is a good quantity to describe the particles, because either you can look it from the group theory, or what you can see is that if the particle is massless, you can never boost to a frame where you are moving faster than the particle. And essentially if the particle is moving slower than you, and suppose initially if the momentum of the particle is aligned along the spin of the particle, if you boost to a frame where you are now moving faster than the particle, then in your frame the particle's momentum is in the opposite direction to the spin. So essentially you have changed the helicity of the the helicity will appear different to you. So for massive particles, since you can do this, the helicity is not a very good quantity to describe. But for massless particles, helicity is actually a good quantity to describe them. Now the point is that initially it was assumed that the neutrino that corresponds to the particular lepton in each generation, this neutrino is massless. Initially it was thought to be that, because if you write down the standard model equations, what you realize is that the neutrino part of the fermion doublet, it essentially does not contribute in the Higgs mechanism. So Higgs mechanism essentially it does not involve these neutrinos. So it will explain the masses of the fermions very beautifully, but the neutrino part somehow it disappears from that. And so what it was assumed was, since the neutrinos mass term is not appearing, the neutrinos should be massless. And I mean, the early experiments also showed something like that, because they were very weakly interacting. So people thought that neutrinos should be massless particles. But later, what it was realized is with a set of various experiments, one of which was to study the helicity of particles emitted during beta decay. What people realized was that for neutrinos, the helicity did not turn out to be a very good quantum number to describe them. So essentially they had mass, because if they did not have mass, then you could essentially describe the beta decay process using helicity conservation and quantities like that. But this was a very rough idea that neutrinos may be massless, may be massive. But the actual confirmation came when people studied the phenomenon of neutrino oscillation. So what was realized was that neutrinos may start off with a particular flavor, which means that a neutrino that corresponds to an electron when it's emitted may oscillate or change its flavor. And essentially when you detect it after some point of time, you might detect it as some muon neutrino. So this is a very weird thing that happens for neutrinos, so that they oscillate in their flavors. And so the point is that if you this oscillation, you can describe this oscillation in a very simple way, essentially using quantum mechanics. And what you end up with is that the oscillation probability or the frequency of oscillation, things like that, all of these depend upon the some quantity that turns out to be the mass of the neutrinos. And so it turns out that since the neutrinos oscillate, it means that they should have mass, because if the mass was zero, then the oscillation probability would have been zero. They couldn't have oscillated. Right. And so this was one of the big confirmations that neutrinos should have mass. But then this is a big open problem in the standard model, that if neutrinos do have mass, how do you describe the neutrinos mass? So it's
Precisely.
obvious that
it's a fermion.
Right,
So
it's a fermion.
you can have two kinds of masses.
Right. So this is a good point. So essentially, Higgs mechanism allows you to explain the masses of the gauge bosons, which again is a cool thing if you think about it. That if a particular thing is a gauge boson, so that's one reason why the W plus minus and Z are not the same as the SU2 generators. Amartya, because if they were the generators of SU2, like if they were the gauge fields corresponding to those, then by gauge because of the whatever gauge transformation and things like that, you can see that the field should be massless, right?
Right.
Because if it's a gauge field, then you can do a gauge transformation, you'll realize that the mass term is not invariant. But we know that
Right.
at low energy limit, the W plus minus and Z have mass. So it means that
Right. Right.
they are not the gauge bosons of SU2, but they are
Right.
Hey,
the
Amartya, a small interruption. What did you mean when you said that a fermion has two kinds of masses?
I'll elaborate once Chetan completes his.
Yeah, okay, sure, sure.
right. So that's one thing that the Higgs mechanism explains. It explains how the SU2 symmetry is actually broken, and since it's broken, then of course the whatever gauge fields will correspond to the this broken symmetry will now acquire mass. And the second thing that it explains is how the fermions themselves acquire mass, like the electrons, muons, and tau. So it very beautifully explains how those acquire mass. But as I said earlier, it like the mass term corresponding to the neutrino essentially disappears, and because of that, you sort of don't know how to describe the neutrino mass. Now, if you think about it, how like what are like how can you accommodate mass for a neutrino? And this is where this the thing that Amartya was saying comes in, that a fermion can have two kinds of mass, and those are the Dirac mass and the Majorana mass. Now, I
Yes.
mean, Amartya, if you want to elaborate on them, you can go on. But like essentially, I can like give a very brief summary that the Dirac mass is essentially, so if you look at the Dirac equation, it's I del slash minus m times psi, something like that. This is your and then the Lagrangian is the psi bar in front of that. So if you look at that, there is a mass term here, right? There is a minus m times psi bar psi. So there is a mass term in the Lagrangian for fermions. So this mass term is essentially the Dirac mass term. And if you say if you have a fermion doublet, so if your psi is essentially kind of a two spinner, so and if like by very uh, basic analysis of Dirac equation, you can see that you can label your these fermion fields by the chirality. So suppose if your fermion field itself is made up of two different chiralities, left-handed and a right-handed chirality spinners. So essentially, what this mass term would be doing is it would be combining the two different chiralities of the fermions. So you will have this mass term will essentially have a term that couples the left-handed and right-handed spinners together. So this is like a signature property of the Dirac mass for fermions. Now, Majorana mass essentially is a like so. I think this Majorana guy, he like very fascinating story. But what he showed was
Yeah.
that there
Very.
was another way of writing down a mass term for fermions that did not have to like. So you did not have to resort to this coupling of the two different chiralities of the uh, fermion, and the way you avoid that is if you show that there is no two different chirality for your fermion. So essentially, if the fermion field itself is like if the charge conjugation of that gives the fermion field itself, which in a different way of thinking means that uh, something that's got to do with PT, and then you can see why it's related to the chirality. So essentially, if the charge conjugate of the fermion field is the same as the fermion field itself, essentially if it's a real, like a real quantity, the real spinner, then what you end up with is a mass term that does not, uh, how do you call it? It does not combine the two different chiralities together, and what you end up with is a Majorana mass term. So this is another way of like giving mass to the fermions, because what you're doing essentially is that you are now positing that your fermions, the fermion spinners are like real valued. So if you essentially have some Majorana fermions in your system, then you can have another kind of mass for them. So this was also what people thought of doing. Like they sort of posited that what if the neutrinos are Majorana fermions? So these are all like essentially the the various models that people have for explaining mass for neutrinos, but so far there is no particular uh, like solution to this problem.
Right. It's
Yeah.
so the thing is, once you so if we start talking about fermions like from a first principles kind of basis, we know that fermions come from the irreps of some Poincare group or whatever, and the irreps are actually not the irreps actually generate your Weil spinners. They don't generate your four component Dirac spinners. And it turns out that now, so generally speaking, the irreps are just psi L and psi R. Now they mix under various things, parity and so on. So which is why Dirac spinner is a more commonly used thing. But the now the thing is, like Chetan said, your Dirac equation, it couples the left-handed and right-handed spinners. So if there was no mass, for example, if the spinner is massless, then the equations of motion for the left and right hand, they just decouple. Now the thing is, the question is, how do you start generating like what kind of mass terms are allowed for your fermion? Now if you now you see, this question would be different for if you're working with a Weil fermion, and different if you're working with a Dirac fermion. With the Dirac fermion, you have four components, and we know that there's a psi bar psi kind of term, and these masses can be generated by a psi bar H psi kind of like a Higgs kind of mechanism. uh, with if you have, however, just by like if you what would be a like Weyl fermion has 2 degrees of freedom, but a Dirac fermion has 4 degrees of freedom. Now the question we ask is there some way to repackage these 2 degrees of freedom into 4? And that's precisely what a Majorana fermion does. And like Chetan said, the condition is that it's a real valued thing in some sense, like the charge conjugate is the same as the fermion itself. So at the like massless uncharged like level, a Majorana spinner will just sort of repackage the 2 degrees of freedom of a Weyl spinner into 4 components. So you can write down, like equations of motion which look like the Dirac equation, whereas the actual like physical components are just 2 as opposed to the 4 that are there in the Dirac equation. Now once you have a fermion with and you start introducing masses, then we know that a coupling like psi bar psi kind of mass, it mixes the left-handed and right-handed chirality. So this, if you expand this out, you get like a psi L psi R kind of mass. So we say that if there is a psi L psi R mixing, then the spinner has a Dirac mass. But however, you can, like, under the assumption that there is like some reality condition and so on, you can also have psi L kind of masses, and these would be just Majorana masses which are generated. Now this is where the fun begins in the standard model. You can introduce a psi L kind of mass by the so-called Weinberg operator. It's a dimension 5 operator, so it's non-renormalizable. But you basically have an L squared H squared kind of operator, and this is, one way to generate a Majorana mass for the left-handed neutrino. You see, this left-handed, right-handed, this language, left-handed and right-handed, only makes sense if it's not a Dirac spinner. I hope you appreciate that, because you don't really talk about a left-handed Dirac spinner and a right-handed Dirac spinner, because the things they mix are like for a Dirac spinner. Like when you say things like left-handed, right-handed, you know that deep down you're talking of 2 degrees of freedom being the physical degrees of freedom. So if you now say that, so now if you have Dirac masses, then you have no problem. The Higgs mechanism, like you have a psi bar H psi kind of coupling, and this generates this mixes psi L and psi R, and this gives you the Dirac mass kind of thing. But if, for example, you commit to the view that, well, actually left-handed and right-handed neutrinos do not mix, and they are some kind of Weyl fermions or Majorana fermions, then the question is, how do you start giving masses to them? So one way is the Weinberg operator, but it's like non-renormalizable, dimension 5, and it gives you an L squared H squared kind of coupling that will generate a mass for the left-handed neutrino. Now, but you see, this is the whole problem with standard model. The standard model has a symmetry called lepton conservation, lepton number conservation. If you have a left-handed neutrino, you should also have a right-handed neutrino. So you must also have a psi R kind of term. But now the thing is, once you have added once you say that, okay, there is a psi L mixing, there is, by lepton conservation also, there must be a psi R mixing. What prevents a psi L mixing? You see, once you have said that both chiralities are there in your action, there is no phenomenological reason yet to expect that there is no psi L mixing. So it's possible that there is even a Dirac mass. So it's very fuzzy to now start giving masses to these things. Another problem, I mean, the group theoretic way to tell this problem, to like describe this problem, is to say that the standard model has a doublet, the electron and the electron neutrino. That's a doublet, and this mixes with the right-handed neutrino singlet via the Higgs. There is no right-handed neutrino in the standard model. So now the way to like get around this is there's a lot of like active uh, open questions basically to how to get around this problem. One is to basically modify the Higgs. That is to say that it's not a doublet but something more than that. The other, which is a little more likable, is that you have another non-renormalizable interaction, just like the Weinberg operator. And this comes from some UV physics, but that's the whole point. We don't know what UV completion of the theory is. We don't know what the fundamental operator will be. But the other way to generate a right-handed neutrino mass would be to say that it just comes out from integrating out some heavier fields in the UV. But you see the problem, right? Once you start introducing like dimension 5 like for example, the way in the standard model the neutrino gets a mass is by the Weinberg operator. But if you've introduced this by lepton number conservation, you must introduce something for right-handed neutrinos. And then how do you discount the possibility that there'll be no psi L psi R mixing? So this is why it's a very fuzzy business. We don't know if the neutrino mass is, like Dirac or Majorana or maybe even both. So yeah. So no, this is why neutrino mass is a funny problem. Another thing, I mean, I don't really know of an answer to this, but I remember having thought about this at some point for a while. You see, there is so fermion like Dirac masses are natural in some sense, because if you take the Dirac masses to zero, then chiral symmetry is restored. So in the 't Hooft sense, Dirac masses are natural, but I've always wondered if there is such a principle for Majorana masses. Like, is there a symmetry that you recover? But probably I'm missing something very.
Actually, there is not. That's why the like leading explanations for neutrino mass involves some kind of Majorana neutrino, where essentially if something is not forbidden, then it should be present. Like this is a very like rule of thumb kind of thing. But there is, go on.
No, but that's precisely the problem, right? If there is no natural reason, so this is why I brought up naturalness, right? Dirac masses are, you can say that they're natural because the symmetry is restored in the limit that goes to zero. Now, if there is no symmetry being restored for Majorana masses, then Majorana masses should generically be of the order of the Planck mass. Then that I believe is the biggest problem with the right-handed neutrinos. Like,
right. So okay, so there is something to that. I'll come to it. But there is a very interesting thing here. Like as you were talking about the Weinberg operator, the dimension 5 operator that you can sort of generate. Like you can sort of write down if you want to see what kind of mass terms you can write for the neutrino. And this is the lowest dimension non-renormalizable operator that you can write. But the problem that you're talking about, that if the mass term that corresponds to this Weinberg operator, if that has a L square term, then you should have a R square term and an LR term also. Now the point is that in standard model, what you see, like what you actually experimentally observe is that you observe left-handed neutrinos and right-handed antineutrinos. So essentially you do not see a right-handed neutrino. Right-handed neutrino is not something that you see, which is very weird.
Right.
You see right-handed leptons. So you see a right-handed electron, you see a left-handed electron, but you never see a right-handed neutrino. Because if
that's what I said, a doublet mixes with the singlet in the standard model, and that's the
because if the neutrino had a right-handed component, say, then you wouldn't even have to resort to the Weinberg operator to explain the neutrino mass, because then it would have been very easy to write down a mass term for the neutrino, essentially a doublet coupling. But since that's not like you do not actually see that in the low energy limit around here,
right.
There are like two possible. No. Right, go on.
Go on, you go.
Achha, so what I was saying is that since you do not see, there are two possible explanations for that. One, there actually is no right-handed neutrino, which sort of seems very weird that you only have a left-handed neutrino. And the other kind of explanation is that there is a right-handed neutrino, there is a left-handed neutrino, and there is a Majorana component to neutrino also. So the one of the very popular models to describe neutrino mass is what is called as a seesaw mechanism. And so this will also sort of allude to your point about the natural masses for neutrino, Amartya. So in the
Right.
seesaw mechanism, what you have is you write down the Dirac mass term for the neutrino. So you introduce a right-handed neutrino, and you write down a Dirac mass term for neutrino. You essentially work with the fact that if something is not forbidden, then it can be present.
It must be there, right?
It must be there. So you write down a Majorana mass term for the neutrino, and you write down a Dirac mass term for the neutrino, and like you have these extra mass terms that you write for the neutrino are essentially what you expect might either be coming from some higher effective field theory, or essentially they are there, but you are not able to detect them in the low energy limit. So if that's the case, the second case is what we expect. Like if they are there, and essentially we are just not able to probe them at a particular energy levels, then it should like this there should be some analysis that explains that, like sort of naturally explains the presence of these particles. Because if you look at the Weinberg operator, what it says is that there is a effective field theory like that
Right.
that's above the standard model, and essentially if you integrate out the heavier fields in the effective field theory, what you get in the other theory, what you get is a standard model, and a standard model plus some extra non-renormalizable terms that correspond to your
Right.
neutrino mass. But that sort of assumes that there exists a UV completion to standard model, as you said,
UV completion. Yeah.
right? So that sort of so essentially that's the point, right? That in the Weinberg operator, the if you look at like dimensionally, if you look at the Weinberg operator, it will be weighed down by the energy scale corresponding to uh,
Right.
the where the breaking happens between the UV completion and the standard model. uh, but like if what we are working with is the fact that the mass terms for neutrino are there, and we are not just able to probe them at the LHC level, what we should expect is from this analysis is that it should show us that okay, there is some natural explanation why we are not seeing them here. And so if essentially what happens is that if you look at just the Dirac mass term and the Majorana mass term for the neutrinos, uh, y- so there is a very beautiful explanation called the seesaw mechanism, which essentially what it does is that you take all these mass terms and you mix your neutrino fields now. So
Right.
what you have is your left-handed, right-handed neutrinos and the Majorana neutrinos. So somewhat similar to how the mixing happens in the electroweak sector. If you mix
Yeah.
your
Exactly.
neutrino fields, what you end up is what you expect is a mass term, that Dirac and Majorana mass term. But if you write down your Lagrangian in the form of those mixed fields, you will not get this particular configuration of masses, but you will get something else. So you will get
Right.
so what you essentially get in those, in terms of those new fields or the mixed fields, or the when you rewrite your Lagrangian in terms of the new fields, what you get is your regular uh, mass for the neutrino. So what you get is your lepton masses, you get your Dirac masses for neutrino. uh, okay, not Dirac masses. So what you get is a mass term for neutrino, and so you get two sets of mass term because you started off with two sets of mass term. You started out with a Dirac mass and and a Majorana mass. But in form of those mixed fields, what you end up getting is you end up getting two sets of masses. One is the Dirac mass for neutrinos, which is a very small mass. Uh, uh,
Right.
the reason why it's very small is somewhat related to when you write it in the form of the mixed fields, your uh, your new mass term essentially becomes a quadratic, like essentially becomes a solution of a quadratic equation. And so in the point is that in your quadratic equation, if you have something like minus b
Right.
plus minus root something discriminant times 2a. So if one of the terms is minus b plus root of discriminant by 2a, the other term is minus b minus root of discriminant by 2a. And if
Right.
you rewrite this in the form of your the parameters that you have, the Dirac and Majorana masses, what you realize is that you can have sort of a configuration of these masses where one of these terms will be very small and one of these terms will be very large. So this is where the name seesaw comes from. That essentially the parameters, the Dirac and neutrino masses are such,
Yes.
like they are
Yes.
essentially such that you have a very small Dirac mass for neutrino, and again a very large majorana mass for the neutrino. So you have two
Yes.
essentially two new particles. One is the right-handed neutrino and the left-handed neutrino, which have very small masses. And then you have a left-handed neutrino that has a very small mass, and you have a right-handed uh, kind of neutrino that has a very large mass. And that sort of
Yes.
gives a natural explanation why a very small Dirac mass for the neutrino will lead to a very large mass for the right-handed neutrino. But
Yes,
so
right. No, so I know of the seesaw I know of the seesaw mechanism, and I know why this happens. But like I said, and like you just said, the right-handed neutrino still has a very large mass. In fact, it's of the order mass Planck mass, and that's
no,
precisely
so
because there is no symmetry coming out from sending it to zero.
right, but but the interesting thing here is that if you, uh, so I've forgotten the explicit calculations, but if you so essentially you have a constraint here, right? That the Dirac and the right-handed and left-handed neutrino
Right.
masses, as I said, they are the roots of some quadratic equation.
Solution. Yeah.
So if you essentially have the Dirac mass for the neutrinos, which you can sort of uh, determine from experimental observations of this
Right.
neutrino
You can
oscillations.
tell what the right.
Right. So you can predict what the mass for the right-handed neutrinos, like the ballpark, the range, order of magnitude. And the interesting thing was that
Right.
the
Right.
order of magnitude turned out to be in TeV range. So people were very excited that, oh, then the 13 TeV LHC would definitely detect some right-handed neutrinos, because
Oh.
it essentially turned out to be in the weak scale.
Right.
So that was the reason why the seesaw model was very
Hmm.
popular, because
Hmm.
one, it gave a very natural explanation for the observed discrepancy in the neutrino masses. Because even if you look at the lepton masses, the lepton mass is still, I think, 3 or 4 orders of magnitude above the neutrino masses. So neutrinos and
Right.
the electrons tau, etc., all of them they are the part of the same doublet, but the electrons have 3 orders of magnitude mass more than the neutrinos, even though they belong to the same doublet, which is sort of like all these kind of problems come under the banner of hierarchy problem, essentially. So the seesaw model gave some natural explanation to the hierarchy problem of the neutrino masses, and it also explained, it was a very beautiful idea. It gave you a right-handed neutrino as you might have expected, and the mass of that right-handed neutrino also turned out to be in the TeV range. So it was a very beautiful idea, but too bad it's
Right.
it does not seem to be the correct one.
Right. Yeah.
So that's
Right.
why.
I just want to stress the point that the right-handed neutrino mass was still very high, and this is precisely why standard model observations so far failed to detect a right-handed neutrino, because it is part of some UV physics. It kicks in at like a higher energy scale,
I
and
think
at a low energy scale where such heavy fields are integrated out.
so
They
that's
are
that's the expectation, I think, that the right-handed neutrino. So that's what I think some sort of experiment this phenomenologists do. So they try to shift these parameters and stuff like that. So they use the LHC data to constrain. So they'll say that, okay, at this up to this energy level, you have sort of constrained all the models. So whatever the mass of the right-handed neutrino, if you consider this particular seesaw model as your model for neutrino masses, then the mass of right-handed neutrino should be greater than this particular limit. So
right.
that's from the explanation, that's from the expectation that this particular model is the explanation. That's why phenomenology is sort of a very, it's I don't
Yeah.
like it, because
Yeah. Me neither.
it's a very weird thing that they do, that they have all these models and then they just sort of end up constraining them and so forth. So
Yeah.
that's sort of why I do not like the high energy phenomenology. But I mean, nothing bad for them. I think they are cool people. Uh, but yeah, it's sort of very experimental work.
Yeah.
So,
Yeah.
but yeah, I mean, this
This
is
was a fun discussion. I've not thought on these lines for a really long time.
I haven't thought about this
Right.
for 2 years, and so there, if I remember
Right.
correctly, there was something very interesting that I just just for fun, I a set of papers that I read before I totally gave up on this project. And that so the interesting thing there was that it was in a sort of intersection between some ideas in let's say that's related to QCD and instantons, uh, sorry, not instantons but axions, to be precise, and the neutrino masses. So what it essentially tried to show was that So I think we talk about the what is this, the reason why you expect a axion in the standard model. I think in some
Yeah,
recent
I think I talked about how you needed to explain parity breaking.
the CP symmetry breaking
Yeah, CB
in
breaking. Yeah,
in the SU3 in the strong sector.
yeah,
But
yeah.
yeah, of course, that's one reason. Like it's a very natural, again, a natural explanation to the CP symmetry breaking in the strong sector, and the mechanism that people sort of that's considered to be the uh, like the mechanism to explain this is, I think it's called the something peak some Pesky and Quinn mechanism, something like that. I might be butchering the name totally, but it's something like that. Essentially, what it does is it introduces so-called Chern-Simons kind of term
Yeah, yeah, yeah.
corresponding to the strong like in the
Right.
strong sector essentially. So this
FF tilde term.
right FF term, right? So it introduces this FF term, which is also called a theta term, I think, due to
Yeah.
something in electrodynamics and condensed matter. So I think
It's called a theta term. Yeah, it's called a theta term because the coefficient is constrained to lie on, it's constrained to be periodic. So
right. Yeah, exactly.
the yeah.
The point is
Yeah,
that
we should talk about this. Yeah.
it becomes the theta term when you look at it non-perturbatively. So if you just look at it at the classical
Right.
level, there
Precisely.
is there is no particular reason why this theta, first of all, why this theta should be a parameter. So it essentially it's a constraint, it's just a constant at the classical level. But if you look at it from a like as a quantum theory, what you realize is that this theta term has to be periodic because of the fact that it appears in the path integral, in the sorry, the action. And so
Right.
like you can sort of see from that it has to
It
be
comes from because the theta term comes as like some theta times FF tilde kind of term, which is a topological
it's a
constant.
topological term.
So if this, yeah, so if, and then you normalize it further so that theta goes to theta plus 2 pi is the exact symmetry as opposed to theta goes to theta plus 2
So
pi
I
by
think
some
the
weird
exact
constant.
mechanism is that since this is a topological term, when you sort of integrate like so, it's like a boundary term, right? It's a total derivative. So if you
Right.
sort of use Stokes theorem here, then it becomes a surface integral of the Chern-Simons form, right?
Right.
Now the point is that if you do a gauge transformation on the Chern-Simons form, it's not gauge invariant. So if you do a gauge transformation on your Chern-Simons form, you will get some. So it will change by some amount, right? And so
Right.
if you do so if your if your path integral has to be gauge invariant, then that's the only possible way that your theta should be periodic, 2 pi periodic. Because otherwise, if you do a gauge
Right.
transformation, essentially your path integral will change. And so that's the reason why, if I remember correctly, the theta term has to be
Yeah,
periodic.
that's one way to put it. I think yeah, that's one way to put it. I think there's I mean, it comes from the fact that it's a first Chern number or something like that.
Oh,
But I think I mean yeah,
um,
yeah. So
I'm not sure if the
I
theta
don't
term is the
yeah.
first Chern number, but the FF term. So essentially, the Chern-Simons form is related to the first Chern number, first Chern class to be precise.
Yeah, right.
Whatever.
First Chern
These are
class.
just like mathematical terms, which
Yeah.
we should not be throwing around. But anyways, the point is that if so now for one, this theta has to be a periodic function, and two, if this actually becomes a local parameter now, what you sort of end up with is axion term. So if you like if you sort of like if you say that this theta is not just a constant or a function, if it's an actual parameter now,
Yes.
degree of freedom,
Yes.
then that's what corresponds to your axial field.
Axiom. Yeah.
So the interesting, so this is what is also like I think it's called the Pesky-Quinn mechanism, whatever. Totally butchering the name. Forgive me for that. But the point is that if you introduce something very analogous to this theta term in the gravitational sector of standard model, if you say, like if you essentially introduce a gravitational theta term, so we know that our like for the gauge fields, the theta term is essentially FF term with a theta term outside. So what if I introduce something of the form theta times RR? That's what that paper was concerned about. Like if you introduce something called as like something that's of the form of a gravitational theta term, theta times RR, what you will get is essentially if you so now what you are working with is some kind of effective theory where your fermions, your standard model couples to gravity at lowest order. So what you'll end up getting is some kind of a term where the fermions will be interacting with the this gravitational theta term, and
Right.
that essentially corresponds to a mass term, and that also in some sense explains why the mass of the neutrinos is very small, because essentially it's appearing from the gravitational sector, and so it will be weighted down by the gravitational constant, and so that's
Right.
one reason why it's a very small mass term. So it was a very beautiful paper.
I see.
I sort of like I read that paper, but like uh, due to the circumstances, I totally got fed up of the field and totally left it. But it was a beautiful paper. So anyone who's interested in this neutrino mass problem, they should definitely check out that paper. Uh, it's by G.R. Diwali, and I think his PhD student at that time, Lena Funky, something like that.
What is the title of the paper again?
Title of the paper is Neutrino Masses from Gravitational Theta Term.
Right. Okay.
Very beautiful paper.
I'll have a look at it. Let's see.
So basically, here the point of the paper is that gravitational theta term. Now, basically, the neutrino masses are generated from graviton loops, so they're suppressed by amp Plankton, so they're very small and so on.
I'm not sure if it's exactly graviton loops. So there is another kind of mechanism where people try to explain. I think Frank Wiczek wrote a paper where he tried to explain neutrino masses using graviton loops, but I don't think that has led to anything. This is a bit different. So Amartya, as you see, this gravitational theta, like this theta term, is essentially a topological term. So it sort of does
Right.
not contribute much to this loop kind of processes. It usually contributes non-perturbatively only. So I mean, I don't know. Like it might correspond to some graviton loops. I might be totally wrong here, but as far as I remember,
Right.
it just
Right.
contributes non-perturbatively.
Right.
But that's the interesting thing.
Also, was this theta term just the Gauss-Bonnet term?
Uh,
Because epsilon RR is, I mean, R like where R is Riemann now. Because that's the topological invariant here,
right. It might have.
right? Because it's epsilon and two Riemanns. That's the Gauss-Bonnet term, and in 4 dimensions,
Right.
it's purely topological.
Yes.
Uh,
Yes.
hmm.
I mean, sure.
But again, but the point is, you usually think of it as coming from some effective field theory. I think we've talked about this Gauss-Bonnet gravity.
Right. Right.
Um,
Right.
right. Yeah.
So
So it effectively comes as Weil times like Weil squared as a Weil squared term.
right. There's this very interesting thing here that so I mean we sort of know that this fermion sector of standard model is essentially a problem in standard model. Like you do not have very good explanations for a lot of things that you observe. For one, like we have the hierarchy problem, and another one is this neutrino masses and things like that. And usually what people like a lot of phenomenologists they are trying to do is you sort of look at beyond standard model kind of theories where essentially you look at higher dimensional operators and you try to see what kind of UV completions of standard model could explain those and things like that. And that's one thing that I might be totally wrong here. Like probably 10, 20 years in the future, this thing will come back to me and haunt me. But I totally feel that this is like that's the wrong path of going along, like thinking about those things, because one thing that I sort of feel sometimes is that this fermion sector of the standard model is uh, like it is something that people usually look at from a particle theory perspective, but it's actually something that people should be looking at from a like gravitation perspective, like from the perspective of gravity. Because if you think about it, if you like see if you sort of look at the similarities between say gravity and gauge theories, right? So if you look at like very roughly, particle theory corresponds to study of gauge theories and things like that, while GR essentially like it involves study of geometric quantities and like sort things like that, like the Riemann Weil tensor and things related to that. But there are a lot of similarities also here. Like there is a way of writing gravity in the form of a gauge theory, in some form of like sense. So
Right.
the corresponding like there is no corresponding gauge symmetry as such, but what you have is a local Lorentz symmetry, and of course the diffeomorphism symmetry of the gravity.
Right.
It's not exactly a local gauge theory in the very precise sense, but there is a way of thinking about gravity also in the form of a gauge theory. So now
Right.
the similarity that I want people to think about very deeply is what we call as charges in the two different uh, models that we have. So in the case of gauge theories, what is the charge for a gauge theory? So for example, if you have electromagnetism, what's the charge? The charge is the electric charge, right?
Right.
But if you look at gravity, what's the charge? So in like
It's the mass.
very rough sense, it's all usually called as the mass, right? The mass is
Right.
thought to be the charge for gravity. But if you think about it, it's not mass that's the charge for gravity, it's the spin. Like it's the spinners that are the charges for gravity. So this
What?
is gravitational forces. So this is something that totally blew my mind, and this was the reason why I like that led me to realize the fact that anything like a lot of the big problems that are to do with fermions in the standard model, they should have some kind of explanation that stems from the gravitational sector of the physics. Because I mean, it's like I wouldn't call it a coincidence. Uh, the fact that neutrino masses are very small, all these hierarchy problems that we have, and then the fact that the spinors are somewhat related to gravity. So this is interesting, and that's why this paper by this Giarduali was very interesting to me. That the fermion masses was arising from the gravitational theta term. Because that's one, like that was probably the only paper that I saw. Like it was the second paper that I saw that was that actually used the idea that whatever this mass problem is, it has to do with some kind of gravitational explanation, and not a very conventional BSM kind of explanation. So yeah, I mean that's something like probably
But you see, Chetan. I mean, this is again cribbing. But the thing is, as soon as you say this has a gravitational explanation, you realize that whenever you couple a particle like a quantum field theory to gravity, you automatically have an effective field theory. So you
right,
must
right, right.
have beyond
Of course.
standard model because
Okay, so I
gravity is not anomalizable.
right, right. So I'm okay. This is like I did not say it correctly. What I should have said is that instead of looking towards some grand unified theory kind of models, we should be looking at some effective field theories that involve gravity also. So of course,
Right. Right.
what we'll be getting is some kind of UV completion that has the whatever standard model with some kind of a gravity theory. Of course, that's correct. So instead of saying beyond sun, because like it's a very broad umbrella statement, but essentially there are two kinds of beyond standard models that people look at. One is the grand unified kind of models where people try to embed the standard model itself in a very large, a larger gauge group. So essentially the SU5
Right.
kind of the Patti-Salam theories,
Right.
then
Right.
some
Right.
SO10 models and stuff like that, E8, E7. So there are all these grand unified kind of models that people look at, and then there are these effective field theory kind of thing where we essentially say that okay, we don't know anything, so why not just look at the properties of effective field theories and see which sort of theories can admit a successful UV completion with gravity and which do not, which is essentially a swampland kind of thing, Amartya.
Right.
And the expectation is that probably we'll end up with a unique set of theories that admit some kind of a completion with gravity, and probably those will solve everything. Like, of course, it's a very
Right.
ambitious statement, but what I feel is that something that's less ambitious than that. Like, you probably do not even require full quantum gravity to explain the neutrino masses and I think the hierarchy problem, because
Right. Yeah.
essentially if you just understand what is this precise connection between fermions and even like low energy gravity, I think you will be able to get some kind of a explanation to neutrino masses.
I think the simplest way to just package all of this information is to say that when you write down the effective field theory of your nature, do not keep your cutoff scale at what is typically kept in particle field theories like weak scale or something. Take it all the way to M blank so that gravity kicks in, and so your effective field action always has a gravity. So
Right.
that's yeah. This I think this is something we can discuss the next time. I can probably talk about this too. The you mentioned the charges and the masses and so on. The weak gravity conjecture is a very, very powerful probing device for looking at things which can be safely UV completed and so on. As it turns out, a lot of the theories that can be or cannot be UV completed are precisely the theories which violate the weak gravity conjecture. This is probably something we can talk about at some time, because I think it's a very simple. Also, sometimes, I mean, in its weakest forms, it's a very useless conjecture too. But it certainly has some importance to it when it comes to charting out the swampland. So maybe we can talk about this at the next time.
Yeah, sure. I mean, it's weird. Like I thought that I was totally done away with this phenomenology and neutrino mass problem, but I end up missing it now.
Yeah, it's a beautiful subject. It's a beautiful subject.
It's actually very interesting, but I don't know. Somehow you like that's one reason why we have this podcast, is it not? Because if
exactly, yes.
It is partial nostalgia in a way.
I mean, it's not just nostalgia. It's like when you start talking about these things, you realize that there was something that you actually liked about it, and this is what you realize when you are actually talking about it.
It was true love,
right?
I don't, right? But this was fun. I think today's discussion was the most entertaining physics discussion I've had in a really long time, because these are precisely the topics I like to think about and talk about. And
exactly,
this reminds me of our days in the main building. Remember, Chetan, when we had started learning quantum field theory, like independently, obviously.
This was exactly what we were talking about in those days.
Yeah, exactly, precisely. We used to sit in front of that board. Santosh used to join us sometimes, but Santosh was not a big main building person, so he wouldn't be there all the time. But you and I, we'd go to that board in front of Thar's office and
I remember,
lecture each other.
I totally remember. I think it was either summer or the winter, some December of 2018, when I was in TIFR, you were in ICER, and I think we used to call each other every week or something, and we used to discuss all these ideas.
Yeah.
Like I think we discussed co-cycles. We have discussed these
co-cycles, anomalies, everything. Yeah.
It was super interesting time, of course.
Yeah, it was amazing. It was amazing. And the thing with Chetan was that he was even more mathematically inclined than I was. So he would send me all these, maths papers to learn about, and it was just a lot of fun discussing these things. It was probably the best part of my life at ICER, those few months.
Well, to think of it, we still have a few months left. Even though
and now I'll be on campus. I'll be on campus with you guys.
But see,
when you guys finally come back, I will be on campus.
I might probably not be on the campus, right? So for me, it's like
you'll come back soon.
I hope. I got vaccinated today, and the interesting thing is that I got vaccinated, and like about 10 seconds after that, I got an email from Microsoft. So, I mean,
what?
I'm not saying that there is something in the vaccine. I'm totally not saying that Bill Gates has put in microchips in the vaccine. I mean, if he has, I think it's time to renew my Microsoft subscription. That's exactly what I got. I mean, I've not gotten this email like in years. Like I have not, what is some kind of renew your Microsoft account or something. I did not get this email even though I was using a pirated form of Microsoft Office. And then all of a sudden today, I got the vaccine, and 10 seconds later, I got an email from Microsoft that renew your Microsoft Office. Talk about the sad aspects now. For the first time, we finished on a happier note. So, I mean, let's finish it. Okay, guys.
Yeah, let's. Yeah.
Right
okay.
then.
Have fun.
Bye-bye, people.
Bye-bye.
See you.
Yes.
Bye-bye.
Bye-bye.